Hey kids, for today, pag-uusapan natin yung differentials and local linear approximation. So let's start with differentials. When we say differential dx of the independent variable x, we are basically talking here about an arbitrary increment or an arbitrary change of x. So basically, kung yung variable x ay mag-change from x0 to x1, then the differential x is just yung difference between x1 and x0. So dx equals x1 minus x0. Then we also have the differential dy. Pag sinabi naman nating differential dy, we are considering here the dependent variable y. So dahil dependent siya, tong differential dy na to, we expect this one to be associated with our independent variable x. And this is given by dy to be equal to f prime of x dx. So later on, I'll show the geometric interpretation ng differentials na to. But before that, let's have some important remarks. Una, if your differential dx is not equal to 0, then the differential dy can be written in this manner: dy over dx equals f prime of x. So what do we see here? Dito sa right side, we have the derivative in the prime notation, so f prime. Tapos dito, we have the derivative na dy over dx. So ano yung nangyayari here? Si dy over dx, nagkakaroon siya basically ng dalawang interpretations. So before, sabi natin, dy over dx is the derivative of y with respect to the variable x. And with that interpretation, hindi natin siya tinitignan as a fraction. Tinitignan natin siya as some sort of a transformation ng ating function na y. So when we say derivative of y with respect to x, we are not talking about a fraction here. However, based on this remark number 1, nagkakaroon tayo ng second interpretation for dy over dx. And that is, yung dy over dx is yung quotient ng differential dy by differential dx. So it depends sa ating interpretation kung tinitignan natin to as a fraction or hindi. Kung derivative, hindi siya fraction. Pero kung tinitignan natin siya in the lens of differentials, then nagiging fraction siya. Geometrically, ano yung sinisignify nitong differentials? So we can look at this illustration here with the blue curve being your f of x, then the purple being the tangent line at the point x0, f of x0. So this one right here, we are considering the point P, which is the point of tangency. Then here at the value x to be equal to x0 plus dx, meron tayong dalawang values na tinitignan. We have the point Q here, which lies in your f of x. Tapos we have this point R, which lies dun sa tangent line. Yung distance between P at saka yung Q at saka R, in terms of x values, ito yung dx natin based on our construction here, no? So when we say dx, that's your arbitrary increment in the x values. So the difference between x0 and x right here would be your dx. Ano naman to, tong distance na to between q at saka p when we are looking at the y values? Ito naman, we can call this as your delta y. And here we can define delta y as the difference between f of x and f of x0. Then similarly, we can look at this distance right here, the difference in y value sa point R at saka sa point P. So, paano natin malalaman kung ano to? Recall. So, recall that at the point x0, the value f prime of x0 gives the slope of the tangent line. Okay? But this f prime of x0, pwede natin siyang isulat as dy over dx. Pero yung dy over dx here, we are talking about this one as differentials. Okay? So, I am specifying here that we are talking about differentials para matignan natin siya as a fraction, no? So, assuming that dx is not equal to 0, if dx is not equal to 0, then we can write the differential dy as f prime of x0 times dx. Pero ano yung magiging interpretation nito? Kung tatandaan natin yung slope, so I can put this here as a side quest siguro. Ang slope ng isang line is rise over run, 'di ba? That's the change in y values divided by the change in x values. Yung change in x values, ito na siya, yung dx. So that means yung rise value should be equal to slope times run. Pero yung slope, it's already your f prime of x0. Yung run natin is dx. So, ibig sabihin, ito, yung rise value, which is actually your dy. So, ito yung dy natin. And what do we see? In a way, pwede nating sabihin na si dy ay malapit-lapit kay delta y. And in particular, kung gagawin ko tong x na to be closer to x0, kunwari dito, we see that yung difference ng dy at saka ng delta y ay mas maliit. So this means that if your x is close to x0, and equivalently, ano ibig sabihin nun? Dahil yung x ay formulated in this manner, x0 plus dx, this just means that dx is close to 0. So, if x is close to x0 or if dx is close to 0, we can say that your differential dy is a good approximator for this delta y right here. So, in a way, this gives us an intuition that our differentials is a good tool in error estimation or in estimating changes. So, itong mga differentials na to, it can help us determine kung ano yung nagiging error when we change our input x, or it also helps us estimate kung paano nagbabago yung ating function habang binabago yung input niya. So, that's how we interpret differentials. So, let's try and use our knowledge on differentials in some word problems. For this first example, the population of bacterium in a nutrient broth is given by this function here, where we are considering the variable t to denote the number of hours after the population is introduced. Estimate the net change in the population within the first 6 minutes. So take note what we are estimating here is a net change. Net change in the population. So since we are looking at P here and we are considering a net change, we want to approximate delta P rather. Delta P. And to estimate delta P, ano yung sabi natin kanina? We can approximate this exact difference right here using your differentials provided that your x is close to your initial value, x naught. So this means to approximate delta P, we will use the differential dp. And for us to use the differential dp, ano yung kailangan natin? What we need here is our initial value x naught, tapos yung ating final value na x. Then we will use this formulation right here that dy equals f prime of x naught dx. So first, we need the differential for our independent variable. For the independent variable, so this time we are considering the differential dt. So take note, our t is defined in the unit of hours, pero ang given sa atin is first 6 minutes. So that means dt natin should be 6 minutes, which is just the same as 1/10 of an hour. So dt natin equals 1/10. Pero tong 1/10, pwede ko siyang isulat as 1/10 minus 0. Ano yung interpretation nito? Yung 0, basically, ito yung ating starting point or starting time for the population. Whereas the 1/10 here, ito naman yung ating running time. So kung titingin tayo sa ating graph kanina, basically yung 0, ito yung starting time, tapos yung running time natin na x, ito yung 1/10. So in this problem, we are looking at our 1/10 as the t value, whereas 0 is our t naught value. So this means that the change in p can be approximated by dp. But what is dp equivalent to? dp is p prime at the point t naught multiplied by our differential dt. So to finish this, let's compute first for p prime of t naught. So given p of t equals 10,000 e to the 0.001 t, we have that the derivative of this one is, naalala nyo pa ba kung paano ang derivative nito? So we have a constant multiple here, we just copy that one. Then the derivative of the exponential is just itself. So we have e to the 0.001t. Pero dahil function yung nasa taas na exponential, we still have to multiply by the derivative ng exponent. So derivative ni 0.001t is just 0.001. And in the end, this just becomes, so merong 3 decimal places here, 1, 2, 3. We have 10 e to the 0.001t. Now that we have our derivative, isasalpak natin dito yung ating value ng t0. So sabi natin, our t0 is t0 equals 0. So p prime of t0 is just p prime of 0, which is just 10e to the 0.001 times 0. So ito class ay magiging e raised to 0 lang, which is 1. So p prime of 0 equals 10. So here we'll have 10 times our dt, which is 1 over 10, giving us 1. So ano yung ibig sabihin nito? What we obtained is that delta P, or the change in the population, is approximately 1. So within the first 6 minutes rather, so within the first 6 minutes, the population of bacterium change by around 1. Okay, I hope this example is clear. So, paano yung process natin? First, you need to identify kung ano yung gusto nating i-approximate. In this case, we want to approximate net change in the population. So, we are talking here about the change in P or delta P. And what we said a while ago is, provided that our T is close to T0, we can use the differential dP. And for you to use the differential dP, kailangan mo muna yung differential for the independent variable. So we have dt here, and we construct dt as the initial point or your starting time, and using the current point or the running time. So dt would just be the current time minus the initial time. So t minus t0. And sabi natin, we are considering the first 6 minutes, which is 1/10 of an hour. And dahil nagko-consider tayo ng first 6 minutes, we can start at t equals 0. So kaya 0 ito, and ito ay naging 1 over 10. Since sabi natin, we have 6 minutes na lumipas na. So I hope this example is clear. Let's proceed to the second one. So the measured radius of a ball is 0.7 inches. If the measurement is correct to within 0.01 inches, estimate the propagated error in the volume of the ball. So this time, what do we want to estimate? We want to estimate the error in the volume of the ball. So we have our function here, which is v for the volume, and we want to approximate the error. So paano natin pwedeng gawing, paano magiging interpretation natin nung error? So if I have a ball here, with radius 0.7, tapos hindi perfect yung aking measurement, then there are two ways to look at this. First, pwedeng sumobra ako ng 0.01. Pwedeng sumobra ako here ng 0.01. Or pwede naman na kulang ako by 0.01. So ito naman ay minus 0.01. And dahil we are considering two changes here, either a positive error or a negative error, that means that yung volume natin, dalawa yung magiging change niya. Pwedeng lumaki or pwedeng lumiit. So, this can be a positive error or a negative error. So, instead of just approximating yung change in volume or the delta V, what we actually want to approximate here is yung absolute value niya. So, bakit absolute value? That is to disregard yung positive or negative error. Kumbaga, parang kino-combine na natin siya, no? So, what we are looking here is just the magnitude of the error. Since same lang naman yung error kung positive or negative. So, to approximate this absolute value of delta V, what we will use, again, is absolute value naman ng dV. So, let's construct everything. So, we know that for any radius r, the volume, since we are considering a ball here or a sphere, we have that V equals 4/3 pi r cubed. So now, we want to identify the differential. So we want to identify first the differential for the independent variable. For the independent variable, which is yung dr. So, how do we determine dr? Sabi natin, yung ating measurement ng radius is correct to within 0.01 inches. So, that means yung ating discrepancy sa measurement ng r ay within 0.01. Pwedeng greater or pwedeng less than by 0.01. So, that means ang ating absolute value of dr here is 0.01. Pero si 0.01, pwede nating tignan in two ways. Since we are starting with 0.7, it's either 0.71 minus 7 or the other way around, 0.69 minus 0.7. So that means dahil ang ating original measurement here is 0.7, itong 0.7 ang aking magiging R0 or yung aking initial radius. Tapos, itong 0.71 at itong 0.69, ito yung aking R dun sa ating illustration here. So, x0 natin is yung 0.7, tapos ito ay 0.71 or the other way around, 0.69, no? So, 0.69, 0.7, 0.71. So, now that we have identified our differential, we have that our absolute value of delta V would be approximated by the absolute value of dV. Pero si absolute value of dV, this is just V prime evaluated at R0 times the change in radius. So once again, let's work this out on the side. So given that V of R equals 4/3 pi r cubed, we have that V prime of R equals 4 pi r squared. And if we evaluate this at our R0, which is 0.7, we have 4 pi times 0.7 squared as our V prime. So, iwan ko muna siya as is. So, we have here equals absolute value of 4 pi times 0.7 squared. Tapos, ang dr natin is 0.01, no? Yun yung error. So our dr here is 0.01, and in the end what we'll get here is 0.0196 pi inches cube. So sir, bakit po pala inches cube yung ating nakuha? So take note, yung dr, this is the change dun sa measurement ng radius. So inches to. Tapos si r naught ay in inches. So we have inches squared times inches. We have inches cube. So what does this mean? So this means that the error in the volume of the ball is within 0.0196 pi inches cube. Okay? So I hope this example is clear, and sana ay medyo nag-grasp nyo na kung paano tong differentials. So now let's proceed to another application of derivatives, which is the local linear approximation. So paano kaya to gumagana? First, let us consider the function y equals f of x and consider a specific value of x, which is x naught. Then we can talk about the derivative at the point x naught. If you will recall, we have defined this one to be the limit as x approaches x naught ng f of x minus f of x naught all over x minus x naught. But since we are looking at a limit, ano yung ibig sabihin nito? This means that provided that x is close to x naught, it follows that f prime of x naught is close as well to f of x minus f of x naught all over x minus x naught. Or equivalently, we have that your f prime of x naught is approximately f of x minus f of x naught all over x minus x naught. So ano yung gagawin natin here? What we want to do is to approximate for the value of f for any given x, no? So what I want to do is approximate this one. Approximate f of x. So what we want to do is to isolate f of x. So to do that, we just multiply both sides by x minus x naught. I get f prime of x naught times x minus x naught to be approximately f of x minus f of x naught. Then putting this on the right side, we get f of x naught plus f prime of x naught times x minus x naught is approximately f of x. So what have we done? Considering this function, f of x, gumamit tayo ng derivative ng f at a certain point x naught. And then, provided that your x is close to x naught, mag-hold itong estimation right here. So take note, this holds only if your x is close to x naught. So, provided that x is close to x naught, we obtain this estimation here for f of x. So, this one right here. So, this one right here, which I will call L of x, is what we call the local linear approximation of f of x given a point x naught. So the function L of x, which is just f of x naught plus f prime of x naught times x minus x naught, is called the local linear approximation or sometimes called the linearization of f at a given point x naught. So, himayan natin itong term na to na local linear approximation. Una, bakit siya approximation? That's because provided x is close to x naught, sabi natin si f prime of x naught ay approximately this one, or equivalently si f of x ay approximately L of x. So, approximation siya kasi f of x is approximately L of x. Next, bakit siya linear? Bakit siya linear? That's because f of x naught, this is a constant. F prime of x naught, this is a constant as well. So, ano yung meron tayo? Si L of x, ang degree niya is 1 kasi we only have an x here na ang exponent ay 1. So that means your L of x is a linear function. Then lastly, bakit meron tayong term na local here? That's because gumagana lang yung ating approximation for values of x that is close to x naught. So, this only works if x is close to x naught. So, local linear approximation, that's because we are approximating the function f using a function L, which is linear in nature, and it only works if your x is close to x naught. So that's the reason why this is called the local linear approximation. Let's try and look at this one geometrically. So una, kung titignan natin yung ating formulation here, if we rewrite things a little bit, si f prime of x naught, this is the slope of the tangent line. Si x naught, this is the point of tangency. Tapos si f of x, you can think of this as your y value. Tapos si f of x naught is yung y naught natin, no? Or yung y value at a specific value of x naught. So in the end, what do we have here? Itong local linear approximation pala, or itong L of x, it's just the tangent line of our function. So kung ito si f of x, ito si x naught, yung L of x natin is just the tangent line of the graph of f of x at the point x naught. And ano yung nakikita natin here? we see that at the point x naught, exactly equal si f of x at saka yung L of x. Tapos, habang lumalayo tayo kay x naught, so let's say, let's consider this portion right here. What we can see is that although hindi na equal si f of x at saka si L of x, we can still say that L of x is close to f of x. No? So when we are considering values not equal to x naught but near x naught, nakikita natin na itong L of x malapit lang din kay f of x. However, kung lumayo tayo further, say banda rito, nakikita natin na lumalaki na yung discrepancy between f of x and L of x. So what we see here is if x is further away from x naught, we cannot assure anymore that your L of x is close to f of x. So ano yung maganda dito? Usually, si f of x, pwedeng degree 2 polynomial, degree 3, 4, 5, so on and so forth. Or worse, pwedeng transcendental siya, no? So, pwedeng trigonometric, pwedeng logarithmic, pwedeng exponential. And medyo mahirap yon, no? Medyo mahirap mag-evaluate kung nagdi-deal na tayo with trigonometric or exponential functions. Pero, dahil dito sa L of x na to, yung pag-compute ng function values na trigonometric, nare-reduce natin into computing function values ng linear functions. And mas madali yun, no? Mas madaling mag-compute kapag linear yung ating function. Ang problema lang dito is, you need to make sure na yung x na pinipili mo, hindi masyadong malayo kay x naught. No? So as long as we are considering stuff that are close to x naught, we will obtain good results. Pag lumayo tayo, probably hindi na maganda yung results na makukuha natin. So let's try and use our knowledge on local linear approximation and approximate the following values. First one, let's try to approximate 2.99 square root of 3.99. So let's observe. Itong square root of 3.99, we cannot compute this manually, no? We cannot compute manually. However, ano yung maganda dito? Si 3.99 is close to 4 and 4 is a perfect square. Is a perfect square. So ano yung ibig sabihin nito? Probably, we can use local linear approximation, pero yung ating local linear approximation is a center natin kay 4. So, kumbaga, yung x naught here is 4, tapos yung i-approximate natin na f value here is f of 3.99. So, gagamitin natin si local linear approximation about the point x naught equals 4, then approximate f of 3.99. So what we can do, so we can approximate 2.99 square root of 3.99, which we will consider as our f of 3.99 by considering the local linear approximation, L of x about the point x naught equals 4. So first and foremost, ano yung gagawin nating f? So kung sabi natin na itong expression na to ay magiging f of 3.99, that means na yung x value natin should be this one right here. So ginagawa natin kasi x equals 3.99. So that means yung nasa loob ng square root, siya yung magiging x. Tapos yung nasa labas, si 2.99, observe na siya ay 3.99 minus 1. Tapos, ito si x. So that means, we can translate this one as f of x. So si 3.99, again, siya yung x. To be equal to, si 2.99, siya yung gagawin nating x minus 1 multiplied by the square root of, so ito naman, tong 3.99 here, magiging x, no? So we can let f of x to be equal to x minus 1 times the square root of x. Then to obtain L of x, ano nga ulit ang kailangan natin? So sabi natin, L of x is just f of x naught plus f prime of x naught times x minus x naught. So sabi natin, x naught equals 4. So ito ay magiging f of 4 plus f prime of 4 times x minus 4. So kunin muna natin si f of 4. We have that f of 4 equals 4 minus 1 square root of 4. So that's 4 minus 1. 3 times square root of 4 is 2. So we have 6. Tapos to get f prime of 4, so differentiate muna natin si f. And to differentiate f, observe that we have a product here, no? So we have a product here. So we have to proceed by product rule. So ang derivative nito is left times yung derivative nung right. So derivative ni square root of x is just 1 over 2 square root of x plus copy the right function, then multiply by the derivative nung nasa left. So derivative ni x minus 1, that's just 1. Then from here, kunin na natin si f prime of 4. So salpak lang natin lahat dito. We have 4 minus 1 times 1 over 2 square root of 4 plus square root of 4 times 1. We get 3 times 1 over 2 times square root of 4 is 2. So we have 3 times 1/4 plus square root of 4 is 2. This one will just end up to 11 over 4. So that means, so L of x then would be equal to f of 4, so that's 6 plus f prime of 4, which is 11 over 4 times x minus 4. So ngayon na meron na tayong local linear approximation, paano natin i-approximate si 2.99 square root of 3.99? Sabi natin, ito raw ay si f of 3.99. And dahil si f of 3.99 ay malapit-lapit, si 3.99 rather, ay malapit-lapit kay 4, that means that f of 3.99 should be approximately L of 3.99. So we have here, thus, our f of 3.99 is approximately L of 3.99, which is just 6 plus 11 over 4 times x minus 4. Sorry. 3.99 minus 4 pala. 3.99 minus 4, which is equal to 2389 over 400. Dito pala, class, it depends kung ang gusto nyong sagot is decimal or fraction. Usually, nire-require na decimal ang sagot. But ako personally, gusto ko fraction. So, we stick to fractions as final answer. To fractions as our final answer. Para medyo mas madaling tignan for me, no? So, let's see how close our answer is, no? Let's open the calculator here. We have that 2389 over 400 is 5.9725. Whereas, yung 2.99, kaya ko bang paanohin to? Ayun. 2.99 square root of 3.99. Explore lang natin, no? Explore. Si f of 3.99 ay around 5.9725203. So what do we see here? Nakikita natin yung ating local linear approximation gives us an answer that is accurate up to 4 decimal points. So as you can see, maganda-ganda yung approximation natin. Bakit siya maganda? That's because yung 3.99 at saka yung 4 sobrang magkalapit with each other. And dahil napaka-close nila with each other, yung L of x mo sobrang dikit din sa f of x as you can see here. So possible, ito si 3.99. Tapos ito lang, si 4. As you can see, what we expect is talagang magkadikit yung values na tinitingnan natin, no? And this calculator shows na napakaganda nga no approximation natin. We obtained an approximation which is good to up to 4 decimal points. Okay? So let's have one more example. This time, let's try to approximate 6 root of 64.12. So, medyo mas overwhelming siya, I guess. So, let's try this one. Observe na si 64.12 is close to 64. Tama? Ang difference lang naman nila is 0.12. And furthermore, yung 6 root ng 64, hindi ko alam kung obvious sa inyo agad. This is just 2. Bakit? If you try to compute si 2 raised to 6, you'll get 64. So, ano ibig sabihin nun? Ang ibig sabihin nun, we can consider a local linear approximation about 64. Kasi, kung gagamitin natin si 64, we obtain a really good number here. Yung 6 root of 64 is a whole number. So, hindi siya ganun kahirap i-compute, no? So, we consider L of x about the point x naught equals 64. So let's figure out how to construct first our function f. So we can let f of x to be equal to, so kung ang gusto natin is that Kung titingnan natin, no, gusto nating i-exploit yung fact na 6 root of 64 equals 2. Pwede natin tong gawing x so that yung f of x natin ay 6 root of x. And kapag sinalpak natin si 64.12 dyan, we get f of 64.12 to be 6 root of 64.12, which is what we want, right? So we can just let f of x to be equal to 6 root of x. Then, yung ating local linear approximation, I have to charge for a while. So then, the local linear approximation, sorry, I'm just using my finger muna, no? Of f about x naught equals 64 is given by L of x equals f of x naught plus f prime of x naught times x minus x naught. But our x naught is 64, so we have here f of 64 plus f prime of 64 times x minus 64. Sana medyo okay na siya. Okay, let's continue. So let's compute here f of 64. So f of 64 is the 6th root of 64, which is 2. Then next, to obtain f prime of 64, kunin muna natin si f prime of x. So take note, si f of x, pwede natin isulat as x raised to 1, 6. So that means si f prime of x is just 1 over 6 x raised to 1 over 6 minus 1. We get 5 over 6 here. A negative 5 over 6 rather. Negative 5 over 6, which is just the same as 1 over 6 times 6 root of x raised to 5. Or pwede rin siya as 1 over 6 times the 6 root of x raised to 5. Then let's compute now f prime of 64. Si f prime of 64 then becomes 1 over 6 times 6 root of x. So that's 6 root of 64 to the power of 5. So we get here 1 over 6 times, ito ay 2. So 2 raised to 5, which when you simplify, we will just obtain, ano makukuha natin here? 6 times 32. 32 times 6, so we have 12. Okay, 192. So we have 1 over 192. So yung ating L of x ay magiging f of 64. So that's 2 plus f prime of 64. So 1 over 192 times x minus 64. And thus, our f of, ano yung gusto nating i-approximate? Again, we want the 6th root of 64.12, which is just f of 64.12, no? Siya ay f of 64.12 lang. 6 root of 64.12. So we have f of 64.12 should approximately be L of 64.12, which is 2 plus 1 over 192 times 64.12 minus 64. Iwan ko na lang sa inyo ulit yung pag-simplify nito. But what we will get is 3,201 over 1,600. Okay? So let's see again kung gaano kaganda yung ating error estimate. So let's explore. Si 6 root of 64.12 ay equal to, so let me enlarge this one again. So we have 64.12 raised to, so ito na lang, 64.12 raised to 1 over 6. We have 2.0006245. Then versus 3201 over 16. Ito naman ay 2.0000625. So tingnan natin kung gaano kaganda yung ating approximation. So tama tayo here, dito, dito. And pati pala dito, no? Tama tayo. So that means, given this 64.12, yung ating approximation is actually good up to 5 decimal points, no? So, as you can see, kahit linear lang yung ating approximation, napakaganda niya, no? It's a really good approximation for our function. So, siguro, before we end, magbigay ako ng sneak peek ng mangyayari sa inyong future subjects. So, sneak peek. Sneak peek. So, right now, so for Math 21, we considered linear approximations for our functions. So maybe a good question is, can we further improve our approximations? And the answer here actually is oo, no? So answer natin is yes, we can further improve. So paano natin i-improve yung ating approximation ng ating mga functions? So we can improve our approximations by considering higher order polynomials. And ito yung tinatawag natin na Taylor polynomials. So we call this the Taylor polynomials. So I won't give the entire details kasi this would require you understanding the so-called infinite series. So kung tatandaan nyo from your high school, nung pinag-usapan nyo yung series, meron yung tinatawag na infinite series where you just keep on adding and adding indefinitely, no? Up to no end. Pero i-limit natin to finite sums. So, itong Taylor polynomials na to, ang ginagawa natin dito to improve our approximation is tinitignan natin yung higher order derivative. So, hindi tayo nakokontento sa first derivative lamang. We are looking at the second derivative, third derivative, so on and so forth. So we can approximate f of x provided x is near a certain value x naught by considering the kth order Taylor polynomial, which I'll call t sub k, I guess, t sub k of x to be equal to the summation from n equals 0 to k ng, so this is how we formulate it. We have nth derivative at x naught all over n factorial times x minus x naught to the n. So maybe medyo abstract siya tignan sa inyo. So let's try to expand kung ano yung nangyayari here. So if we consider n equals 0 muna, we'll get the 0th derivative of f. So that's just our function f at x naught divided by 0 factorial, which is just 1. So hindi ko na isulat. Tapos x minus x naught raised to 0. So magiging 1 lang siya, no? So we have f of x naught here plus the next term would be f sub f1. So that's f prime of x naught all over n factorial. So 1 factorial equals 1. So wag na natin isulat yun. You have f prime of x naught times x minus x naught raised to n, which is 1. And kung titignan natin, hindi ba ito yung ating local linear approximation? Local linear approximation. So ano ibig sabihin nito? That means na yung L of x natin is actually the first order Taylor polynomial ng ating function f at x naught. And kung itutuloy natin siya, dito we'll have f double prime of x naught all over. So n equals 2 na tayo, no? We have 2 factorial x minus x naught squared, so on and so forth, hanggang makarating tayo sa kth derivative of x naught all over k factorial times x minus x naught raised to k. So yung ginagawa natin ngayon na local linear approximation, it's actually just a specific truncation nung tinatawag na Taylor series. So that's your first order Taylor polynomial right here. But if you want to improve your approximations, you can consider the second degree, third degree, so on and so forth, up to kth degree, no? So if you want better approximations, pwede kunwari, you can consider the 100th Taylor polynomial. Pag 100th order yan, in a way, medyo pwede kang lumayo pa sa x naught natin. It might deliver better results. Pero as we can see, no, kahit nasa first order pa lang tayo, maganda-ganda na yung approximations. Pagdating ng second order, we expect na yung accuracy in terms of decimal place ay mas gaganda pa. So to learn more about this, please wait for Math 22 Unit 2. Okay? So I hope you were able to understand the concept of differentials and local linear approximation, If you have any questions, you can message me. Or for those na napadpad lang sa video na to, for those who are not my students, you can leave a comment in the comment section below. So thank you and see you next time.